Welcome to this lectures on Introduction to Algebraic Geometry and Commutative Algebra. So, we have been studying the spectrum of a commutative ring and some of its topological properties. Today I will start a new topic called integral extensions. This is in the beginning it will be algebraic, and eventually I will connect it to the spectrum of the rings. Those who like algebra, they will like this topic very much. So, let us start. So, this is integral extensions. Alright, so to set up the notation, as usual I will say that A is our base ring, and just to remember, it is commutative always with identity, and that identity is usually denoted by 1. If there is no confusion, if there is a chance of confusion, I will denote it by 1a. Alright, ring, and B an A algebra. Alright, so that is our setup, and to be very specific, I will write here with the structure homomorphism phi from A to B, and I will just say that we will allow A, B to be may be non-commutative. So, I will just mention here may be non-commutative. And in that case, we remember that the structure homomorphism has the property that phi of A is contained in the center of B. This is the center of B. This will happen not so often, because very often we will have the ring also be commutative. Alright, so recall that this we have seen earlier also, so I will just say recall that given an element x in B, there is a unique A algebra homomorphism from Ax to B, which maps x to small x, and this I am denoting by Ex. So, this is called substitution homomorphism. Some people also call it evaluation. That is because where will the arbitrary polynomial will go? Arbitrary polynomial with coefficients in A, this will go to f evaluated at x. This makes sense. and we have seen earlier also the image of this map is precisely the subalgebra of B, A subalgebra of B generated by X, and that we are denoting by this. This is A subalgebra of B generated by that element X, that we have seen earlier also. And now we will look at kernel of this. See, because the image we know, this is precisely the image of this Ex. What about kernel? Kernel of this. Now this is an ideal. This is contained in Ax, and this is an ideal. That is because this epsilon x is a ring homomorphism, therefore this is an ideal. Unfortunately, we don't know exactly what is the structure of the ideals in general. If you have a general commutative ring and a polynomial ring over that in one variable, we don't know exactly the structure of ideals there. However, we knew this when A is actually a field K. Then we know all ideals in Kx are principal. And in fact, generated by a unique polynomial if you choose that to be a monic polynomial, and that is where this field play a very important role. But unfortunately we are dealing with arbitrary commutative ring, so we don't have this privilege at our hand, so we have to deal with that. So now let me define. So definition, I use the above notation, no. So what can happen? We are denoting this kernel of Ex. This is an ideal in Ax, and we also know Ax, therefore by isomorphism theorem, this Ax modulo this kernel of Ex, this is isomorphic to the image which is an A subalgebra of B generated by X. Alright, so what can happen? There are three cases can happen. One is kernel of this is 0, 0 ideal. In this case, Ax, the polynomial algebra is isomorphic to the A subalgebra of B generated by that small x. But in this case, and hence we say that small x is algebraically independent, or also some people say or transcendental over the ring A. Alright, second case, kernel of epsilon x is non-zero, that is f belongs to the kernel of Ex and f is non-zero, and because it is in the kernel x kernel of Ex, we know that f of f evaluated at x is 0. In this case we say that x is algebraic over K. algebraic over A. That means it satisfies only a non-zero polynomial. But obviously, how do we find a polynomial actually? That is a big task. So, third possibility is this kernel of Ex contains a monic polynomial in Ax. So, in particular a kernel is non-zero. Kernel of Ex is non-zero, and this is a strong assumption, monic polynomial. Here we did not say f is monic, f is just a non-zero polynomial and it contains non-zero polynomial. Here it contains a monic polynomial. In this case, so let me give a name to that monic polynomial f. In this case, we say that x is integral over A. So, this is very important. So, now we note that if you have a, so note that if the base ring A is a field, then the concept algebraic over K and integral over K these are same, because any non-zero polynomial over a field we can always make monic by multiplying by the inverse of a leading coefficient, which is possible because we have a field, therefore all non-zero elements of that are equivalent, therefore we can do that. But if the base ring is not a field, then both these concepts are not equivalent. And one more thing I will also mention here, normally when one studies what is called field theory or Galois theory, one assumes the field, the base ring is a field and also the algebra is also field. But here algebra is arbitrary algebra and we are allowing even non-commutative. Even I should mention that it is worthwhile to study field theory where only the base ring is a field. The upper ring one should allow arbitrary commutative ring if not non-commutative. Non-commutative is also useful sometimes on especially when you are dealing with endomorphism rings of modules. Alright. So, now I want to, before I go on to study properties of integral elements and more about them, or how to find out some element is integral or not, that is also not so easy, or for example sum of two elements, sum of two integral elements is integral or not, product, whether do they form a subring, all these questions we will answer one by one. But just to connect it with the earlier study what one had done, especially linear algebra, I would like to write this example. So, example, this is basically what we have studied in linear algebra, Cayley-Hamilton theorem. and this I will write down in a general setup. So, again let B be a finite free A algebra, and A is arbitrary, A is base ring, commutative always. I will not write that. Alright, so what does that mean? Finite means it is finite as a modulo over A, and free means free as a modulo over A. Normally all these adjectives, when we add adjectives, we use it for algebra, then what means that as a module. If you say finite type, then it is finite type as an finitely generated as an algebra. So these I have been saying throughout the course. Sometimes repetition is also useful. So I would put this in a base ring in a bracket, a finite free algebra of rank D with basis with A basis x1 to xd. As I said, this B is a finitely generated free module of rank D, and this is the basis. Let me also say, remind you that not all algebras are finite, not all algebras may be free, they may not be free. Alright, so this is our given thing, and for arbitrary element x in B, let lambda x, this is from B to B map, left multiplication by x on B, so that is any y here in B is mapped to yx xy. This is left translation by x. All right, which is clearly alinear. Which is clearly alinear. That means what? This lambda x is an endomorphism of the free module B over A. So this. Alright, now we have more than assumption on B is more, it is an algebra, that means it is a ring also. So you can multiply by elements of the ring B and get another element of the ring B. So for j equal to 1 to D, x times xj, this is also an element in B. So and B has this basis. So this element we write it in the form a linear combination of xi's. I is from 1 to D again, and where these aij's, they are elements in the ring A, 1 less equal to I less equal to, and these aij's are defined for comma j less equal to D. So therefore we can when you rewrite this equation, when you shift to this side and use Kronecker symbol, so therefore what do we get? So I will just say that is summation I is from 1 to D, and this term I want to take it here and absorb here. So that is simple, x delta ij minus aij and whole thing multiplied by x I, this is 0 for all j is from 1 to D. But immediately when you remember your linear algebra, this means So, that will imply by Cramer's rule, I will write here Cramer's rule. What will it imply? Determinant of x small x times this big ED minus A times xi equal to 0 for all j is from 1 to d, and where is ED? Big ED is an identity matrix 1 1 1 1 1 1 d cross d. So, this is in MDA, and this matrix A is this Aij matrix 1 less equal to I, small j less equal to d. This is also matrix in with entries in D. Remember, we cannot use this the matrices with coefficients in A. They are more difficult to handle when A is not a field. For example, to check the invertibility etc. is more difficult to handle. Alright, so this determinant, where is this element? So, determinant is an element when you expand it, it is an element. It is a, when you expand, this is a monic polynomial in x of degree d, and the remaining coefficients which will come from multiplications and additions from this matrix Aij, which is clearly an elements are in A. Therefore, this determinant is a matrix, this determinant is a polynomial in small x with coefficients in the ring A, and that polynomial kills all these xi's, but B is generated as a module by x1 to xd, and identity element of B is also a linear combination of this x1 to xd. So, if this determinant kills all the xi's, it will contain, it will kill one also. In particular, what we will know is, so this I will write on the next slide. So, therefore, determinant x times ED minus A, this is 0, but what is the determinant? This determinant is precisely the characteristic polynomial of lambda x evaluated at x. So, and what is this? This is a monic polynomial in x of degree d. So, x power d plus some coefficients x power d plus a d minus 1 x power d minus 1 etc. plus a1 x plus a0, where a0 ad minus 1 are elements in the ring A. So, we got a monic polynomial which is 0. So, therefore, we know that, so this implies that x is integral over A, because it satisfies a monic polynomial. In fact, what we proved is, in fact, this characteristic polynomial of lambda x, we proved this is in the kernel of evaluation map or substitution homomorphism. Alright, so we proved that in every element, we started with every element. So, that means we proved that every element of B is integral over A. This is what we proved. Alright, so our problem is this was a very natural process which we inherited from linear algebra, but we want to find a good criterion which is verifiable economically to check that when the elements are integral. How do you check some elements are integral? Alright, so that will be in the next proposition, but also I want to introduce a language. The polynomials, non-zero, also monic polynomials in a kernel of Ex are called integral equations of X over A, and we want to know when can we find, when can we see that this kernel contains at least one integral equation, and how do we find the integral equation. The above process shows under the very strong assumption that the algebra is finite and free over the ring A, and we do not even know whether this kernel is a prime ideal, maximal ideal, all this information we do not know. In case of a field, we can get a better information because we are dealing with a polynomial ring in one variable over a field which we know it is a PID, and we also know more knowledge about prime ideals, maximal ideals. They are generated by the prime polynomials and so on. So the next proposition is very important, that will give us a criterion to check when some element is integral or not. So this is a proposition. Alright, so let B be an A algebra. Now we do not have any assumption finite, free, etc., and let X be an element in B. Then the following are equivalent. This is our standard short form, we have been using it all the time. Alright, so what are the equivalent conditions? One of them has to be integral. So 1 X is integral over A. 2, the subalgebra of B generated by X over A subalgebra of B generated by X is a finite A algebra. That means it is generated by finitely many elements as a modulo over A. Then we use the term finite. Okay, third one, the subalgebra generated by X, A subalgebra of B generated by X is contained in a finite A subalgebra of B. This may see note the difference between second and third condition. Here second says that it is a finite A algebra. This one says it is contained in a finite subalgebra of B. Alright. So fourth one, there exists a faithful module over the subalgebra generated by X, AX module, faithful AX module M, which is finite as an A module. So, again let us look at the meaning properly. So, there exists a module over this subalgebra, and faithful means it is annihilator of that is 0. I will write it on the next page, and which is when you restrict this module structure of M to A, that is finite as a module over A. So, let me write that faithful means so. We will prove this proposition soon. So, recall that an A module in general, I am writing general, A module M is called faithful if annihilator of M over A, which is by definition all those elements A in the ring such that A times X is 0 for all X in M. Then you call that is annihilating the module M. Every element is annihilated, so every all the elements in M are annihilated. So, this is if this is 0, we call it faithful if this is 0. So, in other words, that is for each A in the ring A, the homothecy theta A, which is a map from M to M defined by any x going to Ax. This is obviously a linear. This map is injective, and this happens for every A. That means there is nobody here other than 0. For every A not equal to 0, I should have written. So, I will write here not equal to 0. Then such a module is called faithful. Alright, now we come back to the proof. I will write down the easy part, and then the difficult part we will do it after the break. So, for example, 2 implies 3. As I mentioned earlier, this is trivial. 2 implies 3 is trivial, and 3 implies 4. 3 says that, so let me just go and check. 3 says that this Ax is, so first of all 2 implies 3 is trivial, because if this is a finite, the 2, if this is a finite algebra, I would take this, we want it contained in a finite A sub algebra of B, but I will take that itself. So, 2 implies 3 is really trivial, and 3 implies 4, I want a faithful module M which is finite as A module, but 3 says that this is contained in a finite sub algebra of B. So, now I will take that sub algebra which is finite over A. So, that I will take that M equal to that sub algebra, and it is a finite over A, and it is faithful because 1 belongs there. So, nobody else will kill everybody in M. So, I would say here for this proof, take since Ax is a subring of B, Ax, the Ax module alright. So, this is a subring of not B. So, the I should say here subring of C which is contained in B, the X module M equal to C serves the purpose. In 4. See, I just want to show you 4. I want a faithful module over the AX ring which is finite as a module over A, and we have given that it is contained in a finite subalgebra. Let me write here C. So this is a finite subalgebra and this is contained there. So this C is a ring, in particular subring of B, so it contains 1. So therefore that C will be a faithful module over AX, and that becomes very clear. So now it's just matter of tying your concepts together to understand. And now to complete the proof, what we will prove is 1 implies 2, this we need to prove. 2 implies 3 already we have proved above, or it is trivial. 3 implies 4 is also mentioned above, and to complete the proof I have to prove 4 implies 1. So this is these two implications we will prove after the break. So we will resume after the break. Thank you very much.